Uh, Welcome to this course on stochastic modeling. In the previous lectures, we started off by defining the stochastic process as an indexed family of random variables. We also looked at how the index can be interpreted as more often the time or the spatial coordinates, and we saw it can be one or multi-dimensional. We then looked at how the random variables that comprise the stochastic process can be as either discrete or continuous. With that, we classified the stochastic process into 4 categories, namely the discrete parameter, discrete state stochastic process, and so on, all the way up to continuous parameter, continuous state stochastic process, 4 kinds of categories. Then we saw that a simplest characterization of the stochastic process is possible as a collection of independent identically distributed or IID random variables. To make it more realistic, we saw that we can have a stochastic process which only remembers the present information, and for any prediction of the future characterization, present is enough, and past states that are being traversed are irrelevant, and that we call it as the Markov property. And using the Markov property as a default nature of the stochastic process, which is what is mostly encountered. So the Markov stochastic process can be again classified into 4 categories, again based on the nature of the index or time and the state space of the random variable. With these introductions, we are going to get into the first category of the stochastic process that are widely encountered in modeling, namely the discrete time Markov chain. We will abbreviate this discrete time Markov chain henceforth as DTMC. So let us first quickly look at this title of this class of stochastic process and understand it well before looking at its characterization and properties. First, it is a discrete time. So the index or the parameter is mostly treated as the time variable in this class of stochastic process, and the time is discretized. That is, I can identify a time point which may stand for a trial or a sample or an experimentation, and we use non-negative integer to associate it with these time points. The exact time intervals between the sample points, sampling, or the trials are not relevant, but only the ordering is relevant. Therefore, we will call it as the first trial, second trial, and so on. And that is what we mean by discretizing the time. So that tells you about the first 2 words that appear in the DTMC. Next, it is a chain. By that we mean that the state space of the stochastic process is finite or countably infinite. That is, the random variables that we talk about in the stochastic process are discrete random variables. We already mentioned that instead of using the qualification process, we use the term chain whenever we are dealing with stochastic process which have a discrete state space. It is just a matter of convenience or convention that we follow. Chain in one sense tells that there is a discrete number of state space, and it can jump from one state to another state. So it's like a chain of states over which the process switches as time progresses. So what finally remains is the Markovian property, and we have to now understand the Markovian property in detail before we proceed into the discussion of the discrete time Markov chains. For that, let us start considering an familiar experiment which we have been dealing in the previous lectures also. It is nothing but a sequence of Bernoulli trials, for example conducted using a fair coin. Two possible outcomes are possible, head and tail. Because it is a fair coin, the probability of getting head equals the probability of getting tail equals to 0.5. An example realization of the process can be of this one which is given here, string HH, TT, HHT and so on. But this is a sequence of events. Now we introduce the notion of random variables, because instead of dealing with events, it is rather easy to or mathematically more convenient to deal with random variables, because there we deal with numbers, and therefore algebra can be used when dealing with numbers as compared to dealing with events which are nothing but subsets of a sample space. When we deal with these things, events, we have to use set algebra, whereas when we deal with random variables, we can use the ordinary algebra on the real axis. So we associate a discrete random variable. For example, to the event that the head occurs, we can associate a number 1, and to the tail we can associate a number 0. For example, we may interpret, again the interpretation can be varying. We can interpret that if a head occurs, we have a gambler who wins the particular trial in the gambling process and gets 1 unit of money. Whereas if the tail occurs, the trial is lost and no money is gained. That way the random variable signify the amount of gain, profit made by the gambler in each trial, 1 or 0. There are many other ways of defining random variables, up to our convenience. We can define +1 as the value of the profit gained whenever a success which is associated with the head occurs, and -1 or a loss of 1 unit of money whenever the tail or the failure occurs, and so on. So this way of assigning a real number to a particular event for the sake of defining random variable is up to us, and it is not going to change the nature of the stochastic process. Then we look at the sequence of Bernoulli trials. Corresponding to the sequence of outcomes or events that can occur in a particular realization. By that we mean you conduct one sequence of trials and look at the event and the values of the random variable for that particular sequence. So we call that as a realization. Every time we conduct, we get one particular realization or other. So we will associate the random variable x1, x2, x3 as the random variable corresponding to the event that has occurred in the first trial, second trial, and so on. So x1 takes the value 1 when head occurs with a probability 0.5. x1 takes a value 0 when tail occurs with a probability 0.5. x2, x3 are similar in nature. So in that way, x1, x2, x3 are identically distributed. All are Bernoulli random variables which are independent of each other. and identical in characterization. So based on a particular realization of the events, we can get the particular realization of the random variables. For example, in this case, it can be 1 1 0 0 1 1 0 and so on. So as we saw that x1, x2, x3 are independent and identically distributed Bernoulli random variables. Okay, so this is a very sort of a very simplistic random stochastic process, and we would be interested in little non-trivial stochastic process which can capture reality, which can be used for real world modeling. To this we take one step which is closer to realistic modeling and define what are called as the Markov processes. To this end, what we will do is we will look at what is called as the cumulative profit obtained by the gambler after a given trial. We will call that as S, the cumulative profit, and after the nth trial it will be denoted as Sn. So Sn is the cumulative profit obtained until and including the nth trial. Therefore, because n again can take non-negative integer values, we have got S1, S2, S3 and so on, which are all the cumulative profit obtained after the first trial, second trial and so on. And again we have got a collection of random variables. Again they can be indexed using the same n. So just like x1, x2, x3 is a stochastic process, which we can call it as xn, n is equal to 0, 1, 2, 3. Sn, n is equal to 1, 2, 3. Of course 0 may not be relevant. 1, 2, 3 or collection of stochastic process. Of course, if you want, you can define S0 as one where the profit is when no trial is conducted and therefore the profit is 0. We know that the connection between Sn and Xs. Sn can be written as x1 plus x2 and so on to xn. Now we will talk about the stochastic process Sn. What is the nature of the state space, index parameter and so on. So the state space of Sn, okay, are nothing but the values the random variable Sn can take. We know that Sn can only take values 0, 1 up to n, because we talk about the profit that is obtained, which can be 1 or 0 in each trial. Negative profits are not obtained. So negative numbers, integers are not allowed. Of course it has to be integers. And the maximum profit obtainable after the nth trial is n, so it is 0, 1 up to n. So if you look at the state space of Sn, it is discrete, non-negative integer values from 0 up to n. So it varies from n to n. For Sn it is up to n, for Sm it is up to m and so on. So the state space differs from one random variable to another random variable in the collection or in the family of random variables. But we saw that we would like to have random variables in a stochastic process which have the same sample space, which are defined on the same sample space, and the nature of the random variables also, if it is the same, then we can talk about the relationships in a stochastic process. So we would like to have typically the state space of the stochastic process to be the same. So here the value taken by the random variables change up to n for Sn. In one way it looks like their state space are different, but we can always come up with the state space which is applicable for all Sn, for all n. How? By taking the allowed values of the random variable to be all non-negative integer values going up to infinity. So it can be 0, 1, 2 all the way up to infinity. Of course, we know that for Sn, values beyond n can occur only with 0 probability. But that doesn't matter while we are defining the state space. It is the same state space for all processes, but some of the state values have 0 probability. So that way we can define a probability mass function which is valid. So this is just for convenience, and for uniformity we assume that all random variables S1, S2, S3 have the same state space, which are all non-negative integer values. So we have now a collection of random variables or family of random variables S1, S2 to Sn, and whose state space of 0, 1, 2 onwards, and the index parameter is n, which is again non-negative integers 0, 1, 2 and so on, which stands for the first trial, second trial, third trial and so on. Therefore, Sn, n equals to 1, 2, 3 and so on is a stochastic process. It is discrete index stochastic process, and it is a stochastic process with discrete state space, so we can call it as a chain. So it is a discrete time chain. But is it a Markov chain? That is what we are going to probe into. We know that xi's are IID random variables. What does that mean? That is, probability that x4 equal to a given value small x4. Note, capital X4 is the random variable x4, that is the outcome of the Bernoulli outcome of the fourth trial. Small x4 is the value it can take. It can be 1 or 0. Given that the random variable x3, x2, x and so on are given. So the probability that x4 equal to small x4, capital X3 is small x3, capital X2 is small x2, is just probability that x4 is equal to small x4. That simply follows from the IID nature of the random variables, because x2 and x3 are not going to influence the outcome of x4. So this is what we know. But we would like to verify what will happen for such conditional probability measures for Sn, and look at it whether it satisfies the Markov property. So what we know that if Markov property is obeyed, the conditional probability that S4 equal to small s4, S3 equal to small s3, and similarly for S2 will be such that S4 will only be dependent upon the random variable which has occurred at the latest time point. Here we know the ordering is 1, 2, 3 onwards. So given 2 and 3, 3 is the present information. Given the present, the past, that is S2, is irrelevant for predicting S4. So this is what we look for. In order to look at that one, first we will notice that Sn at any given time can be written in a recursive manner as Sn minus 1 plus Xn. So we know that Sn can always be written as sum of two random variables, Sn minus 1 and Xn. Okay, and these two are independent of each other, because Sn minus 1 is x1 plus x2 all the way to xn minus 1, and each one of these random variables in this collection or summation is independent of xn. So these two themselves are independent of each other. Now we will probe into the Markovian property of the Sn process. First, we will look at and look for certain conditional probabilities. Before that, let us concentrate on a particular random variable S6, say, which is the outcome cumulative profit obtained just after the 6th trial. So before we even start the experiment, if you are asked the question, what are the values which S6 can take with non-negative probability, you can tell it is 0, 1, 2 all the way up to 6. And if you are asked a specific question, what is the probability that S6 equal to 4, without giving any information about the values of S1, S2 and so on, that is even before you start conducting the Bernoulli trials, you can of course find S6, because S1, S2 are all binomial random variables. It's a sequence of binomial random variables. You know, they have the binomial PMF. Okay, so what will be S6? What is the probability S6 equal to 4? For that to happen, there has to be 4 heads which should have occurred in 6 trials, which means there has to be 4 heads and 2 tails in any order. So it is nothing but 6 choose 4, probability of head, which is 0.5 power 4, into probability of tail, which is 0.5 power 2. So we can find out. Similarly, probability S6 is equal to 0, 1, 2, everything can be found out. Now if you are given some information, that is, you have conducted 4 trials and therefore you are able to find out S4, and it is found to be 3. With this knowledge, if you want to recompute the probabilities of S6, how do we do it and how do we represent it? Now we do it by using conditional probability measures. We write it as probability S6 equal to some value given S3 equal to 3. So now these conditional probabilities will be the new probability measures, because they are all computed using this condition which is known to have occurred, and we will use this information to compute the probabilities. Okay, so we know that all these values are the one which can be recomputed. We will just go through it. What is probability that S6 is 2 given S4 is 3? That will be 0, because the profits are 1 and there are no losses. If you do not win, we get just 0 rupees. So we will never go down in the value of profit obtained. Having got 3 unit of money in 4th trial, we can never get down to 2. So it is 0. What is this? S6 is equal to 4 given S4 is equal to 3. For this to occur, there is just one more head that would have occurred out of the 2 trials. So one head out of 2 trials, it can occur in any possible manner. We have 4 possibilities: head, 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 tail, tail, head and tail, tail, out of which we are looking for 2 possible events that can occur. Each of these events can occur with a probability 0.25. Head, head is 0.25, tail, tail is 0.25 and so on. So it is basically 2 out of 4, which is again 0.5. So that way we can compute. Similarly, if you look at this one, S6 equal to 6 given S4 is equal to 3, this can never occur, because we cannot gain 3 units with 2 trials pending, 0. This one, if you look at 3, 3, this is possible only when we don't get anything. only tail should have occurred, and whose probability is 0.25. And similarly, you can see that from 3 to 5, if you want to go, 2 unit of money would have been obtained, which will occur when 2 heads occur out of 4 possible combinations that can occur. So it is 0.25, and again this is 0. So we can compute conditional probability measures. Now what we do is we go ahead and conduct the 5th trial. And in the 5th trial, this is a newer experiment. Okay. So what we do is we know the value obtained in the 4th trial, and then we also do the 5th trial and also know the value obtained in the 5th trial. Together with these two information, we now predict the value of S6. And those values are all is the one which are given here. That is, suppose in the 4th trial we have got 2 unit of profit, and 5th trial 3 units have occurred. Together these two, if you want to make use to predict S6, how well we can do. Again you can see that this would be 0, having got 3 you cannot come to 2, and here it means that what this tells is that is the 6th trial has to result in a head whose probability is 0.5. So this is what you will tell. So see here we know that for this a head should occur, but that inherently assumes that S5 is equal to 3. This information is used in order to tell that just we need an head to get this state. So only we have used these two information. Nowhere this information is used. This is now irrelevant. If supposing if S4 is equal to 3 and S5 is equal to 3, and then use that to recompute this, then also we would get the same answer. So which means that given this, we could write it as probability S6 is equal to 4 given S5 is equal to 3. This can be dropped. So this is what we mean by the Markov property. As we see here, this is what we mean by the Markov property. Similarly, if you look at this one, this would be 0, 3 to 6 cannot occur. Similarly, 3 to 10 cannot occur. 3 to 5 occurs with probability, it cannot occur, and so on. So 3 to 3 means this is how it can occur, and so on. So what we understand from that is, similarly, if you ask higher, if you conduct up to 9 tosses, and we note down the profits obtained in various time points, to predict the 10th one, that is S10. What is the probability S10 is equal to some number given S8, S6 and S5 and S3? We would clearly tell that S5, S3, S5, S8 are not. S8 is the only thing that is relevant to predict S10. All previous one are not relevant. So this clearly exhibits the Markovian property. So this Markovian property is the one that we are going to make use of in analyzing the discrete time Markov chain. So we saw that Sn can be written like this one. Sn minus 1 and Xn are independent of each other. Xn is also independent of all the previous random variables. So, sorry, we have this has to be Sn. Sn is a DTMC. So what we can now do it, suppose we ask they have the we are looking for conditional probabilities of the form. What is the probability xn plus 1 is equal to some value given xn is equal to this one? Okay, so the or probability of this form, it is given at one time point, we would like to have it at the subsequent or a future time point. First we will concentrate on how to get these conditional probabilities. One thing that we know is, if on this side, that is after the, along with the condition, if we have more time points, then we can retain only the latest time point and drop the other things. So nowhere we need to look at cases where x n plus 3 is equal to something given x n plus 2, x n plus 1 and so on. We can always, only we need these kind of conditional probabilities. That is why we are interested in finding the conditional probabilities of this nature, where this is at one time point n, this is at a future time point n plus k for some arbitrary k. If k is equal to 1, then it is a one step ahead computation. We will now look at a case where we want conditional probability of this kind. Given xn equal to I, what is the probability that xn plus 1 equal to j? So these such probabilities are the one that we are interested in. Because we are going to work with these probabilities extensively, it is better to come up with a shorthand notation so that our writings and analysis will be more clear. It may not be very cumbersome. So we use this shorthand notation, wherein we use subscripts and superscripts. Subscripts are used to stand for the state space of the stochastic process we are talking about, and the superscripts are used to stand for the time points. So again, the way we write it is former state space followed by the later state space reached, former time point followed by the later time point, which we talk about in the conditional probability. So here n is the former time point, n plus 1 is the later one, former state is I, later state is j. So it goes from the time point n to n plus 1, from the state I to the state j. So to denote it, we use like this one. So in the subscript, I comma j has to be used. In the superscript, n comma n plus 1 has to be written. The way we can read it is probability that the DTMC goes from the state I to state j in the time point n to the time point n plus 1. So here I and j can only take values in the state space, n and n plus 1 can take values which are discrete time values. It can it's non-negative values. Now we can talk about processes wherein this conditional probability, again to begin with we will only concentrate on unit step conditional probabilities. Probabilities in going from one state to another state in one time step. Okay. That itself may be dependent on in which time from which you make the jump or the transition. So we will use the term transition. By that we mean we go from one state to another state. That is what we call as the transition. By step we mean from one time point to the next time point. So these probabilities can in turn be functions of the time at which the jump or the transition takes place. That is, Pij n plus 1 can be different from Pij m plus 1 or m plus t for an arbitrary t. So for a generic stochastic process, these probabilities can change as time progresses. But we know that most of the cases in reality we talk about processes which has reached some sort of stationarity. The notion of stationarity will be made more formal later, but we have an intuitive understanding of what we mean by stationarity. That is, we have a physical phenomenon which the variables governing the physical phenomenon has been kept constant, so that the dynamics of the process, physical process, is stabilized and it is not going to change. For example, if you keep some thermodynamical variable constant, thermal equilibrium will be attained, and afterward it will be in stationary state. That does not mean that the values are exactly predictable, but the statistical prediction will not change. So if a process has reached that kind of stationary condition, we will call such stochastic process as time homogeneous process. For a time homogeneous DTMC, Pij n plus 1 are independent of n, which means that in place of n, if you put m, Pij n plus 1 will be equal to Pij m plus 1. So henceforth we will deal with only time homogeneous discrete DTMCs. Unless otherwise mentioned, we will assume that the process is time homogeneous. Well, thus for a one-step transition probability, we will, that is wherein we go from one state to another state in a time point n to n plus 1, we will call these as one-step transition probabilities. So what from the Markovian probability that xn plus 1 is equal to some value, small xn plus 1, given xn, xn minus 1 and so on. We know that from the Markov property, xn plus 1 will only depend upon xn, and these xn minus 1 are all irrelevant, and therefore these conditional probabilities or even these probabilities can in turn be written like this one: probability xn plus 1 in from n to n plus 1. But we know that these are all independent of n because of the time homogeneous nature. So the actual value of n is not significant. So we can drop it and use a much more compact notation where you will just include only the time step, which is 1 in this case. So let us again this one instead of xn, small xn plus 1, which is a right way of telling that the values realized by capital Xn and capital X1 plus 1, we will use the notation ing, and then therefore these conditional probabilities xn plus 1 equal to j given xn is equal to I, we will call it as Pij, and in the superscript we should have 1. And again, for convenience, if you know that we are only talking about one-step transition probabilities, even this 1 can be dropped. We can simply write it as Pij. But in case we talk about multi-step transition probabilities, whereas we go from I to j from n to n plus t, then although n is not significant, t is significant, and therefore this t should be retained in the superscript to denote the time step involved. So this is the shorthand that we will henceforth use. One more characterization that is important is that at any given time, the Markov DTMC will occupy one state or another, and you would like to know the probability that it occupies a given state at a given time. Those are called as the state occupancy probabilities, and we can put all such probabilities for all the states in the DTMC together in a form of a vector, which is called the state occupancy vector. We will use the notation P0, P1, P2 to stand for the probability that state 0 is occupied, state 1 is occupied, 2 is occupied, and so on. We will put them together in the form of a vector and call it as pi. If we use the probability of occupancy at a time t, then this state vector is for the time t, state occupancy probability for the time t. So the t is also important to signify that this is the state occupancy at the time t. At a different time t, these may change. We know that pi, I0, 1, 2, 3 are nothing but the probabilities present in the probability mass function of the dt, of the random variable characterizing the DTMC. So these are nothing but the list of probabilities present in the probability mass function. So pi indicates that state I is occupied at the time t. If you want to be more clear, you can also put a time as the superscript of these probabilities. We will now look at the case of the IID Bernoulli random variables, that is x1, x2, x3 and so on. So for which, if you look at want to compute the conditional probabilities, that is I, the former state can be +1 or -1. Okay, this is for a case where we have +1 corresponding to the success and -1 corresponding to the failure. The next state j can be +1 or -1, and probability that you will this is a sequence of Bernoulli trials, and the stochastic process we talk about is xn, n equal to 1, 2, 3. And you know that for this is not a DTMC. For this process, the probability mass function is fixed and does not change. Given I is equal to +1, the probability that j is equal to +1 is p, and it is fixed. And j is equal to -1 is 1 minus p, and it is fixed. And it is the same whatever value I takes, whether it is +1 or -1. So it is always p, 1 minus p, irrespective of the value of I. This is how an IID process will behave. Okay. So with this, now let us, in contrast, we will see how the one-step transition probabilities of the SN process, that is the cumulative profit stochastic process, will look like. We saw that we can compute the one-step transition probabilities Pij for given two states I and j. Inherently, we assume it is one step. That is why the superscript 1 is dropped. So let us try to club all these conditional probabilities, one-step conditional probabilities. We will later show that these are the only things that are relevant to completely characterize the stochastic process DTMC, apart from the initial state occupancy vector. So we want all these probabilities, Pij's. So how many such conditional probabilities are there? Now we can vary I and j independently. So it is, and if we have a stochastic process which has got n possible states, capital N possible states, I can vary from 1 to n, j can vary from 1 to n. So there will be n squared such probabilities will be there. We want to put them in some form so that we can easily remember how we have structured it. Obvious way is to put it in the form of a matrix. So we will come up with a matrix of Pij's. We will call them as the state transition probability matrix. and in particular they are all one-step transition probabilities. So we will have a transition probability matrix. So again, unless otherwise mentioned, a transition probability matrix corresponds to a one-step. We can also have a multi-step transition probability matrix. So for this Sn, n equal to 1, 2, 3, where Sn is the cumulative profit obtained by the gambler, where success corresponds to a profit of 1, failure corresponds to a profit of 0, then the state transition probability matrix will look like this. Okay, so suppose you are in 0, with the probability p, the fortune will go to p. So what we are doing is, we arrange I stands for the row, j for the column. I can go from 1, 2, 3 all the way up to infinity, because we allow the game to continue without ending in this case. And so j can go from 1, 2, 3 and so on. Or for example, we will start with 0, because a 0 profit if it is also allowed. Then if in the first one trial, if you have a loss, your profit will remain as 0, and if you have a gain, it will go to 1. So that is why we have indicated 1 minus p for 0, 0, and p 0, 1, it is p. 0, 2, 0, 3 are all not possible, so they are all zeros. Suppose we are in a case where the profit is 1, profit can never become to 0, so that 1, 0 is 0, 1, 1 means there is no profit being gained in this trial. So it is 1 minus p is the probability of that happening. With the probability p, we will gain 1 more rupee, and from 1 we will go to 2. Similarly, from 2 we can go to 3 or remain in 2. Other values are not reachable, states are not reachable. So we will see that this is how the transition probability matrix will look like for Sn. Now we will now look at a problem which is very a classical problem which has been widely analyzed while developing the probability stochastic modeling process by the mathematicians in the when in the early days of the developments. It is called as the gambler's ruin problem. It is very similar to the gambling process that we talked about earlier, but we will slightly we can modify it. So what we do is, we have a case where a sequence of Bernoulli trials are being conducted. Each trial can result in a success or failure. Based on that, the gambler will get a profit or a failure or a loss. And the probability of success is p, and probability of success is p, and probability of failure is q, which is 1 minus p. And these success and failure probability do not change with the trials, which means that the successive Bernoulli trials are independent process, and it is also identical. So this is basically an IID stochastic process, but we construct a Markov process based on this one, wherein we look at, first we will define these random variables corresponding to this IIDSP. x1, x2 and so on is plus 1 if the gambler wins with the probability p, minus 1 if the gambler loses with the probability 1 minus p. Now we will call Sn to be the cumulative profit obtained by the gambler, or total fortune of the gambler after the nth gamble. What is the fortune? we talk about fortune is defined as the cumulative profit that the gambler has obtained. Sn is equal to x1 plus x2 and so on. We will assume that initially the gambler starts off with no fortune. That is S0 is equal to 0. But this is not necessarily have to be the only way. We can start off with any arbitrary fortune. That is, the gambler goes to the casino with some money, call it as I or some S, and then starts playing the game. So here, if you look at that, the value Sn after the end of the nth trial can take values which can be positive, 0 or negative. It can become negative because, in general, okay, it can become negative because losses can also sequence of occur. But to make it more meaningful, we will put some rule in the that will generally be followed by a casino. That is, anyone who plays should be such that if they lose, they should be able to give the money to the casino. Suppose a gambler plays when the fortune is 0, that is, there is no money with the gambler, and if the gambler loses, he will not able to pay the casino, and therefore, because of this eventuality, the casino will not allow the gambler to play the game. What it means is, once the fortune hits 0, the game has to stop, because in the eventuality of the loss, the gambler will not be able to pay, and the casino is not interested in such a situation, so they will send out the gambler. Well, but the gambler can keep playing as long as the fortune is non-zero, positive non-zero number. But for the benefit of the gambler, we can assume that a gambler would be satisfied when the fortune hits a fairly large value, say capital N. Because once this large amount is obtained, the gambler is satisfied. The gambler is not interested in taking any more risks. He would like to stop the game at any given time and then he can leave. So the gambler comes with a mind of stopping the game once the fortune reaches N. So this is a classical problem of the gambler's ruin problem. So the initial fortune can be anything, and the game stops when the fortune either hits 0 or a given value capital N. Then we can come up with a transition probability matrix for a gambler ruin problem. So I will show it in a different lecture, but you can take it as an exercise and then come up with how it will look like. And here you will have certain cases where certain probabilities will be 1, okay, P00, Pnn are all 1, which means that once we go to a state, we will not be able to come out of the state. And such states, we will call them as absorbing states. Now we will look at another case where we have a communication channel wherein bits get transmitted. At any given time, we can transmit a bit numbered 0 or 1, and because of the nature of the communication channel, bits may be corrupted. In particular, bit can be flipped. A 0 can be converted to a 1, or a 1 can be converted to a 0. And we would like to model the way the communication channel behaves statistically. So we've come up with one of the simplest stochastic model in this course, and so what we do is we send a bit at one point at the transmitter end and we receive the bit at the receiver end, what is the probability a bit that is sent 0 will arrive as 0 itself, and what is the probability it will arrive as a flipped bit 1, and so on. So given this, the probability that a bit gets flipped to be p, and so p is the probability that error will occur. 1 minus p will be the probability that error will not occur. So if you span the column and rows using 0 or 1, which is the values the bits can take, which is also the value a random, suitably defined random variable can take, a probability of a 0 being transmitted reaching as 0 is 1 minus p, that is no error. 0 getting converted to 1 is the probability of error, which is p. And if we assume that this error probability is the same for whether the bit is 0 or 1, then a bit 1 getting converted to 0 is p, bit 1 remaining as 1 is 1 minus p. So this would be the transition probability matrix. Okay. So note that if you add these two numbers, okay, we get 1. So incidentally here, if we add across the column also, we get 1. Note this carefully. We will later on define certain properties of this transition probability matrix. We will show that row sum has to be 1 for all matrices, TPMs. But if column sum is also 1, they are special kind of matrices called as the doubly stochastic matrix, but it need not be a condition that has to be enforced. Now we will go one step ahead in coming up with a stochastic model for predicting the occurrence, which is a very simplistic weather prediction model. We would like to predict whether on a given day whether it will rain or not. So we want to know whether a given day, tomorrow will it be a rainy day or it will be a sunny day or a no rain will occur. So we will use a symbol to make it shorthand. R to stands for a rainy day, N to stand for a no rain day. So what we can do is we can observe a sequence of days and note down what happened in that day. A sequence can be n, n, r, n, n, and so on, that will indicate whether no rain, no rain, rain, no rain, and so on. So these kind of observations constitutes a stochastic process, because on any given day in a future we don't know what is going to happen, whether it will be rainy or sunny, but we can always make a prediction based on a weather prediction model. So that is what we want to come out with. So someone who has been observing these patterns can first come up with a very simple model. The model basically what it does is, based on what happened on a given day, we make a prediction for the next day. This is the simplest possible model we can have. So on a given day called as the present day, it may be R or N. It might be a rainy day or a day with no rain. The next day can be again R or N. So there are 4 possible combinations that are possible. So 2 possible values, the random variable or the events can occur. So we have to find the conditional probabilities for that. Of course, these conditional probabilities are to be guessed based on the expertise of someone who are able to come up with the model. So we will just use a loose notation of x n plus 1 is equal to r. These are not random variables because they have to take only real values. We will use the symbolic notation r itself for that, r or n for that. So suppose a model tells that if it rained on a given day, the probability it will rain on the next day is 0.8. Or if it didn't rain on a given day, probability it will rain is 0.3. And if it rained, probability it will not rain tomorrow is 0.2. Given that it didn't rain, it will remain the same in the next date is 0.7. So these are all something which someone proposes out of the expertise in weather prediction. So if you ask a question, where does this number come from? Is it possible to derive these numbers? The answer is no. This is outside the realm of stochastic process. Based on the domain, nature of the domain and some other physical characterization and so on, someone has to give this one. What we can do by using this is that we will be able to make prediction of what will happen 10 days from now. Or given that in the 7th day it rained, what will happen in 15th day. Those are the things we can do. But this is something that has to be given to us. And also we assume that it is possible to make a complete prediction of a future date given the value of the what happened on a given day, present day. And these predictions will not depend upon what happened in the past days. That is what happened 3 days before that and so on. That is, we inherently assume that the process is Markov in nature. But it need not be true. But this is one of the simplest model that we can think of which makes the prediction easier. So the modeling may not be so accurate, but still to some extent it allows us to predict. So the Markovian nature that we enforce on this process makes prediction possible, but it has a limitation. So what it means is we can put them in a compact matrix form, state transition matrix. Rain is 0.8, rain, no rain is 0.2 and so on, based on from the probabilities that has been given to us. Rain is 0.8, rain, no rain, this is rain or n, that is what how we put it. R is 0.8, or n, R to n is 0.2, that is you have to carefully note which is I and which is j and accordingly do it. NR is 0.3, NN is 0.7. But now you can come and then tell that okay, this is not a good prediction model, because if you are given what happened in the past 2 days, I would be able to make a better prediction. It's likely, because it might be such that because of some change in the cloud pattern, sporadically on a given day it might have rained during a summer, then it is not possible probable that it will again rain. But if you know that it has been raining for 2 days, if you don't know about the seasonal changes in that particular geographical area, we only know what happened for the past 2 days, that will give an indication whether you are in summer or in a rainy season, monsoon season and so on. So if it rained in past 2 days, it is very likely to rain in the next day also. Or if there are no rains in the past 2 days, it will likely not to rain in the next this one. So a better model can be obtained if the process behavior depend upon the past 2 days information. That is, probability that xn plus 1 is equal to small x1 given xn is equal to xn, xn minus 1 is x minus 1 is not equal to this alone. If you adopt this model, the process is no more Markovian, because past or history is also relevant for predicting the future. So which means that if you go in for this more realistic model, we lose the Markovian property and all the mathematical framework that we are going to develop in this lectures will not become useful. What do? Fortunately, what we can do is, we can still come up with a way of modeling this phenomenon by embedding this so-called non-Markovian model and replace it with a Markovian model. What inherently we have been doing is that we took the state space of the random variable, which tell whether it rained or not, as R or N, and given that state information R or N, we predict the future possible state R or N. Now we expand the state and now redefine that we always keep track of the what happened in 2 given days, in a day and its previous day, and that we call it as the state. If we do so, then we always have got as state what happened in 2 given days, and we make use of this state in predicting in the 3rd day. This is called as the expansion of the state space. But when we do that, the process can again be put within the Markovian framework. So now what we do is, we have a state which is the as a pair of characters that indicate what happened in 2 subsequent days. Rain, it can take the following values: RR indicating a rain followed by a rain, RN means a rain followed by no rain, NR means no rain followed by a rain, NN means no rain followed by a no rain. With this, we would like to predict what will happen in the future and present. But note that we are on a given day, n and n minus 1th day, these are being defined. When we move, we have to again retain information about 2 days, which will be n plus 1 and n. So the nth day information which is present here will also be present here, but it will be the previous day when we come here. Because of we know what happened on the nth day, and that information should be preserved when we come up with the probabilities of the new one. Certain states may not be reachable. Okay. So here you look at, it tells that it was rained on, it was yesterday it rained and today also it rained. Now we want to know what will happen in the next 2 days, that is tomorrow and today. But we know today it rained, and therefore we cannot go to a state as nn, which marks that today it is n and tomorrow it is n. So these are not reachable. So sorry, n followed by r and n followed by nn are not reachable, because this n which is present as r here tells that these are not compatible with this information. So now one can come up with the model for this. For example, here you have, we always, as we have mentioned, we keep track of what happened in 2 given days. We treat it as a window which maintains the information about 2 days, and we slide the window 1 day at a time to come up with the model or prediction for the next day. So a given day will be present in the states of 2 successive states. So again, if someone can give this transition probability matrix, we will be able to compute. So what in summary we are trying to tell is that it is possible in many cases to embed a non-Markov model into a Markov model. In case if you want to make the model more accurate and treat 3 days weather information to predict the future one, still we will be able to use expand the state space further and come up with a model. Only thing is the TPM, transition probability matrix, will be a much larger one. So this is the primary reason we see that why Markov models are extremely useful, because in most of the real world situation can in turn be brought into the Markovian framework and be handled. So we will stop at this point. We will look at more, we will develop theory of how this transition probability matrix can be handled for making predictions. Thank you.